And you can run these PowerPoints yourself. It's a left mouse click. This little icon at the very bottom sort of looks like a camera. If you click on that, then the PowerPoints will run. And let's see if I can make this a little bigger for you guys. And okay, that's probably big enough to see. All right, so let's begin. And we're going to look at matter and measurements during this introductory part of the course. And we'd have to start out, I guess most scientists start out with defining who they are. And what's chemistry? Well, chemistry is a study of matter and how it's made up and the energy that is associated with changes in matter. These things we call chemical reactions. So we're looking at all kinds of matter. Matter is anything that has mass and volume. And so that covers just about everything. All right. So matter does have to have both of those two properties. It has to have mass and it has to have volume. I'll show you a simple consequence of that requirement in a moment as well. And you can find matter in a gaseous form. And if we think about a sample of gas, now that wouldn't be a gas. All the particles are touching each other. But what would happen in a gaseous sample is the particles would be in continuous movement. They would be moving from place to place, bumping into each other, bumping into container walls. And it's this bumping into the container walls that creates what we call pressure in a gas. So every time those molecules bump into something, then that's going to impart a momentum against that surface, and that will result in a force that we refer to as pressure. But one of the things you need to notice is that gases take the volume and the shape of the container they're in. So no matter what container they're in, if it's in a bottle with a lid on it, it'll stay in the bottle. If you take the lid off, it will diffuse out through that opening, and it will take the shape of the bigger container, maybe the room you're in, and it will eventually cover every single speck of space that's available to it. It's the way gases work. Now, if you look at a liquid, liquids we could model like this. The particles would be touching each other, and they would create a little puddle down in the bottom of the container. Now, it takes the shape of the container that it's in, but it doesn't take the entire volume. The liquid is going to have its own volume, and it'll have a property called density. For example, if that's water, there's 1 gram per cubic centimeter. 1 gram per milliliter is the density of water. So a 1 gram sample of water would fall into that container and take up a volume of 1 milliliter within the container. Now, notice the particles are touching. So if I want to put a pressure on liquids, you see, I'm not going to be able to change the volume very much because the particles are already touching each other. But in gases, I could compress that gas into much, much smaller volumes. I'm sorry?
I'm sorry I woke you up.
Okay. You maybe need to turn your mic off unless you want to address the class. Okay. All right. Now, for solids, we can model the solids like this. You imagine the solids would arrange themselves into a very ordered pattern. And now this is at an atomic level. So you're talking about atoms lining up across the edges, and they will form extremely sharp corners. But the thing about solids is that every particle, the one I'm pointing to right now, this one here on the top left, never moves from that spot. Now it does move. It's vibrating around in what would be like a little cavity, but it can't get out of that cavity. And it's got a certain amount of kinetic energy within that cavity, just like the gas has a certain kinetic energy, amount of energy by motion that it has. It moves over much, much greater distances, and the particles can go anywhere. Any single particle can be anywhere in the whole volume. In the liquid, the particles are in the bottom of that container, remember? They can't get out of that bottom of the container, but they can move from one place to another. You do have diffusion in liquids. It's much, much slower than in gases. So you can imagine there's a sort of a cavity around the liquid molecules as well. It's the individual molecules are bouncing around within their own little cavity, but every once in a while they'll hit with enough force that they'll bump into the next cavity and move down the line. And the others move in the same way. That doesn't happen in solids. You don't get diffusion of particles in solids. They're permanently arranged in this very ordered pattern. Sometimes we call that a crystal lattice. I'm tracing now some of the crystal planes in that molecule. Here's one right here too, see? If you take every other one, you got this one and this one and this one, you see? You've got planes of atoms at different orientations. And we'll look into this in more detail a little bit later on. But that's unique to the solid state. Now, here's the thing that books don't often tell you, but when we talked about the kinetic energy of molecules, the kinetic energy is defined as 1/2 mv squared, mass of the particle times the square of its velocity, is the kinetic energy. The kinetic energy of a gas or liquid or a solid, doesn't matter which, is directly proportional to its absolute temperature. So if I'm talking about a solid that's at 25 degrees, or a liquid at 25 degrees, or a gas at 25 degrees, all three have the same kinetic energy, irregardless of what they are and irregardless of the phase. Books don't tell you that, but that is true. The kinetic energy is actually 1/2 mv squared for any substance is 3/2 R times its temperature. R is a constant. We'll talk about that later as well. Okay, so you can see that we've got for solids a definite volume of the solid, and it has a rigid shape. It has its own personal shape. Different solids arrange their particles inside in different patterns. We'll look at that in detail in Gen Chem 2. And one of the things I think you would have noticed in the discussion so far is that matter is made up of individual particles. Matter is particulate. In our case, when we talk about elements is the simplest form of matter, and there's a handful of them. There's well, if you count the ones we've made, I think there's 109 altogether, or maybe 114 or so. About upper 80s of those naturally occur. So if you just took a sample of dirt from the earth, and big enough sample, you would find about 80 some odd elements possible within it. Each one is a particle. Each particle is different from each other particle. For example, hydrogen particles, atoms, are different from oxygen or nitrogen or carbon or copper or nickel, each one of them has its own individual type of atom, but they all exist as atoms, particles. Matter is particulate. And the particles have most of the time when we talk about textbooks, we sort of give the implication that all the atoms are little spherical balls. Well, they sort of pack like that, but that's not the story. Each one of those particles has a different size, may have a different shape, does have a shape associated with it. For example, carbon atoms like to form compounds where the carbon atom has four things attached to it in a very ordered pattern we're going to call a tetrahedron. So oxygen tends to hold two things to it and hold them at an angle that's close to 109 degrees. So atoms actually do have a shape when they begin to combine with other atoms. So they have a different shape and they have a difference in the way they pull charges to themselves. And we're going to look at, that's called electronegativity. We'll look at that later on. But the point I'm making here is that all matter is composed of particles. The simplest particles we call atoms. And those particles have different sizes and different shapes and different ways in which they attract other charges to them. So they must come together in very distinct three-dimensional shapes. And the shape of everything you see around you is pre-programmed into the atoms that make it up from the moment of creation. The possibility of building a structure of proteins and amino acids and all the stuff that you are is the result of the atoms that make you up. And they were created with a solid, with a shape and a size and all of the characteristics needed to put molecules together in the extremely complex system that you are. And everything around you can have those shapes because the atoms had that shape that allowed that to happen. Isn't that cool? Now, at the same time, we're going to talk about energy a little bit later on. I mentioned that in the definition as well. Let me tell you something about energy. Energy is also corpuscular. Energy doesn't come to you as a flowing stream of continuous energy flowing from one place to another. It doesn't happen like that. If you've got a hot object, it's got extra energy in it, and so it's going to dissipate that energy. But the way it does it is by releasing particles of energy. Energy is made up of particles. We're talking about light. We call those particles photons. And in any sample of energy like that, you're going to have individual particles of energy, just like in any sample of matter, you had individual particles called atoms. We have those particles of energy as well. So energy is itself particulate, but there's different kinds of energy particles. For example, if we're talking about photons, then you can have red photons and green photons and blue photons and pink and purple. You can have all different colors of photons. Each one of those of the same color would have the same kind of atoms, just like, or particles, just like in, if you had a sample of copper, you'd have lots of different copper atoms. The copper atoms would be different from iron atoms, but the copper atoms would all essentially look alike, just like the red photons all essentially look alike, and so forth. So energy has its ability to transfer from one place to another uh, at a fixed speed called the speed of light. And so energy is made up of particles as well. Now, I'm going to I'm going to stretch your mind. I don't want to blow it, but I do want to stretch your mind. Um, Now, what about space itself? Is it particulate? And the answer is yes, it is. The very space that you're in is made up of extremely tiny specks of space. Just like in that picture we had of the solid, it was made up of little particles touching each other. Well, the same thing is true of space. Space is made up of little individual particles. There's a here and a there, and there's nothing between here and there. There's an atom of space here and an atom of space there. There's nothing between. It's just one speck after another in 3 dimensions. Now, the specks of space are also different from each other. They differ by size, and very important. If we had no matter in the universe at all, there would only be one atom of space. It would cover the entire universe because we've got nothing in there. We don't need to define an edge or anything like that. But if you've got a star somewhere in that space, then what's going to happen is the space particles themselves get tiny and get smaller and smaller and smaller, depending upon the amount of matter that's present. And you know what that does? That creates what we call gravity. A particle turned free into space will be attracted into the region of space. It'll flow downhill towards smaller particles of space and be attracted to other massive objects. The more massive the object is, the tinier the atoms are, and the stronger the, quote, gravitational force is. So, there's a plan there that we do have particles of space, and by them having the characteristics that they have, it creates what we call gravity. Now, I don't want to blow your mind again, but I want to stretch it again. What about time itself? There's a tick and a tock, and a tick and a tock, and there's nothing between tick and tock. There is a time particle as well. Let's call it a moment. There is a moment of time. Now, moments of time also vary in size. For example, if an object is traveling at the speed of light, its time has only one moment. It covers all of eternity, from beginning to forever, if you're traveling at the speed of light. Now, what's the consequence of that? It means time doesn't change when something is traveling at the speed of light. You can read these stories about, for example, the twin brothers who were, let's call them identical twin brothers, who one was an astronaut and one was not. He stayed at home with his job. But the astronaut tells his brother, hey, I've got a mission. I'm going to be gone for 20 years. And so I want you to come back and meet me 20 years from now. And so he goes out into space, and his brother waves him off at the spaceport. He travels at 60% of the speed of light and returns. All the time he's gone, his heartbeat is, let's say he's real healthy, it's 60 beats a minute. And his brother is too. He's very healthy. His heart is beating 60 beats a minute. When the astronaut gets back and looks around, his brother, he didn't find him at first, and finally he shows up, and he said, the guy who stayed home says to his brother, so I thought you said you'd be gone 20 years. I've been coming here, you know, sometime during the day, almost every day for 20 years now. You were gone 40 years. And sure enough, when the astronaut looks at his brother, he sees an old, decrepit guy who's got arthritis and everything. And when his brother, who stayed at home, looks at the astronaut, he sees him, you know, like a 40-year-old guy. So that while we can't actually do that experiment, the math is correct. So when something travels at the speed of light, its time doesn't change. When you take a picture with your camera and you send it off out into to a friend, say several states away, well, it's going to be converted, that image is going to be converted into photons of microwave energy. It's going to be transmitted to several different towers between here and there. And it finally arrives at your brother at the speed of light. The image you sent is exactly the same as the one he receives, because nothing is changing when time doesn't change. So the image that you send, and if it missed your friend and missed some of those towers, you know what? It's going to go out into space. And if it's ever captured anywhere in space, that picture is going to be exactly the same as the one it sent it. And if you could ride on that picture, you could arrive at that spot without changing at all. You would still be identically to who you were when you left the source. Those things can't happen, but photons do travel at the speed of light. They all, no matter what color they are, no matter what size they are, they still travel at the speed of light, and time stays still for them. Now, let's summarize all of this. We have matter, energy, space, and time. The fundamental concepts of everything, and they are all patterned exactly the same. How's that possible? How in the world would that be possible? Well, you know my answer. God made everything, and he used the same pattern for it all. That is so cool. Okay, all right. Now, when we look at matter, we find it in nature sometimes as pure substances, not often. It's usually a mixture of pure substances. When they found gold in California, I heard the story that someone sort of tripped over a great big nugget of gold, is where how gold was discovered. That gold was pure gold. Wasn't mixed with anything else. But most of the time, when we find matter, it's going to be a mixture of some kind of pure substances. The substances are elements. We've talked about those. There's, like my periodic chart I'm looking at, it's got 109 of them on it. That's the simplest form of matter. It could also be compounds. And a compound is going to be a union of two or more elements. Now, this is a statement of the law of definite proportions that was due to Joseph Proust. And before him, John Dalton had reasoned that whenever you have chemical reactions taking place, that you just move atoms from pairing up with one element to pairing up with a different one. And he postulated that matter was made up of particles. Proust looked at that and saw a relationship that was testable. And that was that a compound always contains the same elements combined in the same proportion by mass. We'll be doing a lab experiment like that later. Now, the result of this is that matter is the same no matter where you find it. If you've got table salt, it's going to be the same no matter where it's located. If you find water somewhere, it's going to be the same no matter where you find it. If it's in a puddle, or if it's in the ocean, or if it's water vapor from in the air, or rain water, or whatever, it's always going to be the same. It's always going to contain only hydrogen and oxygen, and the ratio will be 8-to-1 by mass. There'll be 8 times as much mass of oxygen as there is mass of hydrogen in water. So when we look for water in NASA's looking for water in outer space as an indicator of potential life, they can tell whether a crater on the moon has water in it or not, because they can analyze it and see that it has all the same properties of the water we find here on Earth. It also means that natural and synthetic compounds are really identical if they're both purified correctly. Excuse me. Now, here's the first incident of a checkpoint. And what I would like for you to do during the break is pull up the, if you can do it without losing Zoom, pull up the checkpoint number 1 for the from D2L, and we'll work on it. It will look like this. I don't know whether it's exactly the same numbers or not. It may be different. I change them periodically because since they're part of grading, sometimes students just pass them on to each other from previous classes, and that way they don't have to work it out. But you don't also learn the concept when you do that. Here's a compound called sodium sulfate. It contains sodium, sulfur, and oxygen. Some of you may already know what that formula is. But here's a true example. If I took 1.5 grams of sodium sulfate and decomposed it, what I would find, it contains 48.48 grams of sodium, 0.34 grams of sulfur, and 0.68 grams of oxygen. Now, let's work some problems with this. This is an analysis that shows a total mass of sample and the masses of each of the elements that would be in that total mass. If you add these up, all of these should equal 1.5 grams. What mass of sample would you need in order to have 1 gram of sulfur? Now, this is a procedure we're going to use for working problems. We're going to take the problem amount that's given here, 1 gram of sulfur. So 1 gram of sulfur. And now I'm going to do what's called a unit conversion. All I'm going to do is multiply that by a conversion factor that gets rid of grams of sulfur and goes to grams of sample. And I put the data. If I want grams of sulfur to cancel, so that needs to be in the denominator. I want grams of sample in the numerator because that's what it's asking for here. I set it up so that the grams of sulfur will cancel and I will have grams of sample. Now, the reason why this works is it doesn't look like it, but 1.5 grams sample is equivalent to a sample that has 0.34 grams of sulfur in it. So essentially, the numerator and the denominator of this factor is 1 when you take the units into consideration. So I can multiply anything by 1 and not change its true value, but I do change the unit in doing it this way. And that's the way we do all conversion factors. You'll have an amount given in the problem with a unit given in the problem. Put the unit given in the problem in the denominator of your conversion factor. Look back at the problem and put the unit needed in the numerator, grams of sample. And now look for data that connect those two. A 1.5 gram sample has 0.34 grams of sulfur. So I can do that math. And then I get that answer. So 0.441 would be the answer. if I had that many gram sample, it would have 1 gram of sulfur in it. Okay, now there's problems like this, or there may be a different one on D2L. That is your checkpoint 1, okay?
Before we head off, checkpoint 1 actually isn't working. It's coming up saying the file associated with the content topic cannot be found.
Okay, all right. I see I've got some stuff to do. I thought I had those all uploaded. You do see the checkpoint though on D2L. It just doesn't have anything in it, right?
Yeah, mine's popping up. It's just empty inside.
Okay. All right. Well, I'll fix this, and we'll do this checkpoint later. I don't quite know why that happened. I uploaded last spring's sample that did work. Okay, I'm just thinking too much out loud. Okay, let's go on. All right. This would be a good time for us to take our break, I guess. It's a little past 8:30. So if you'd like to take let's say we will reconvene at 20 minutes till 9, okay? All right. So, and let's stop this.
Hey, Dr. Pearson, real quick while we're taking the break.
Okay, it's time for us to get started back. Okay, we've had talked about the fact that natural and synthetic compounds are identical. It really doesn't matter what the source is. For example, aspirin is a compound called acetyl salicylic acid. And if you make aspirin if Dow Chemical makes aspirin from synthetically in the lab, or you take willow bark and extract the compound from that, it still will help a headache no matter which one you use. And I'm not going to fall for the hype and advertisement of picking some little particular brand of aspirin. I can go to Sam's Club and get the 200 bottle for a few bucks, and I'm not going to be paying $5 or $6 for a little tin that's got 12 tablets in it and has little bees on them. So it doesn't matter much. I did check online and saw what you told me, and as soon as class is over, I'll go and fix all those files. I thought they were already uploaded, but evidently it just loaded the shell and didn't load in what I had in them last spring. All right, so we'll fix that. That's not going to be a problem. And when we get checkpoints today, what I'd like for you to do is go ahead and print them out from D2L and work them out individually. And I tell you what, for the ones we do today, just photograph it and send me the photo at my email address. That's not the way I really want to do it, but let's do that for the ones we get to today, probably number 1 and 2 anyhow.
I don't have access to a printer, so can I just write it by hand?
I'm sorry?
I don't have access to a printer, so can I just write it out by hand? Is that okay?
Yeah, that's okay. Now you will need access to a computer though when you do your exams and quizzes. Is that going to be a problem?
No, just the printer part.
Okay, all right. No, it doesn't matter much how you do it. You can write it out by hand. You can, hey, pull it up on, oh, you said you didn't have your computer.
No, I
Instead of
have
telling
a
you to put it
computer,
up
but not a
on the computer and take a screenshot, but that's
Okay.
okay. However you
Yeah,
do
my-
it's fine. Just send it as an email attachment to pearson@mtsu.edu, and I
Okay.
will then grade these all by hand, and we'll come up with something better maybe by tomorrow.
Perfect. Thank you.
Okay. Now, how do you?
I have a question.
I remember vividly in graduate school, my organic professor coming in to the class one day, all excited, and he held up a little vial between his thumb and his first finger, and it had little yellow crystals inside the vial. And he said, "Ladies and gentlemen, I'm holding in my hand the only sample of this compound that exists anywhere on Earth. It's not been made ever before, and I made it, my graduate students made it in our lab, and here's a sample of it." And I still think about that and think how exciting that is, to be able to make something that nobody else in the world has ever seen before and do it in your own lab with your own research skills. So I was very much impressed by that. But how in the world did he know that nobody had ever made that compound before? Well, you describe every pure substance has its own set of chemical and physical properties. Now, chemical properties are the way things react. For example, combustion is often listed as a chemical property. The compound will burn in air. Well, I don't think I'd want to do that if I had the only sample that exists in the world. I probably wouldn't use that chemical property. And I probably wouldn't choose to use any chemical properties, because that's what happens during a chemical property measurement. You destroy the sample. And sometimes it's okay to destroy just a little of it. Maybe you could take one crystal and see if that would burn. And he had a vial full of them, so maybe that would be okay. But chemical properties tell how things react, and they are destructive. The best properties are physical properties, because they just give physical descriptions. Okay, for example, he had that compound in his vial, and it was little yellow crystals, solid. So he could eliminate a lot of things. Of all of the thousands of gases known at room temperature, it's not one of them. Of all of the liquids known at 25 degrees, it's not one of them. Of all the solids at 25 degrees, it's not the blue ones, it's not the green ones, it's not the colorless ones, it's only the yellow ones. It's one of those, perhaps. Then you can do things like melting point. Where would it melt? Okay, so you melt it, and you watch the temperature as you heat it up, and you note the point where the crystals start to break down and dissolve and melt, and then when the last one melts, and you give that as a temperature melting point range. And so say it melts at 38 degrees Celsius. Well, maybe you start seeing melting at 37.5, and it's completely melted by 38.5. So maybe you say it's in that range. Well, all the things that melt less than that, it's not one of them. And all the ones that melt at higher temperatures, it's not one of them. And all the ones you heat up and it decomposes before it melts, it's not one of them. So by the process of elimination, you can narrow things down dramatically. And if you add to that the chemical intuition of my professor, he knew the reactants he put together, and he knew from good chemical principles the list of compounds that possibly could have been made. And then he's looking in that list for one that matches his compound and didn't find it. So he was pretty sure and published the work, and referees agreed with him that this was a unique new compound. So we identify elements by their chemical and physical properties. We do our science by a method called the scientific method that involves making observations. It involves looking for patterns within the observations. See if you see things that are similar in groups within all these observations that you made. You would group them and find the ones that are similar to each other. That's a pattern that you've seen in those observations. Then you look at that and see if you can explain why these are all in the same pattern and why this pattern is different from that one. And this is a guess. It's called a hypothesis. So you make a guess as to why this pattern exists and what it means. Now, here's a critical part of the scientific method. And anything that can't do this is not a science. You have to be able to test your hypothesis. It has to be a real physical test. It can't be a mental test. It can't be of, well, it's obvious that. No, no, no. It has to be a physical test. If this hypothesis is true, you can predict the result of this test. And if you're correct, then your hypothesis gains in insight, and people begin to believe it a little bit more. And if it keeps being tested over and over and over again, and everybody then says, you know, this is just generally true, then we call that a law of science. And you have to do the testing by experiment. And I can tell you now, there are theories around that have never been tested experimentally that we put a lot of emphasis as if it's really true. But you know what? It's not true if it's not experimentally tested. Sorry about that. Okay. Now, in order to do our laboratory work, we use a system of measurements. It's called the SI system, System International. We have various things we measure. We measure mass. In the SI system, the standard unit of mass, the base unit of mass, is the kilogram. It isn't the gram. Most of the time we do lab work, we measure things with a gram balance and convert to kilograms if we needed to. But the base unit for SI, for mass, is a kilogram. It's given the symbol kg. For length, the mass unit, the basic unit, is the meter. Not the centimeter, not the millimeter, but the meter is the base unit. Time is seconds, and we do use that one. Temperature is kelvins. Now, the Kelvin temperature is really the Celsius temperature plus 273.15. And the Kelvin degree is the same size as a Celsius degree. So if you had a Celsius thermometer, you could just just add 273.15 to each of the numbers, and that would give you the Kelvin temperature number. Generally, we don't do that on the thermometer itself. We just measure it in Celsius, and then we add 273.15 to calculate the Kelvin temperature. And I still have trouble with this, but they don't say degrees Kelvin. They say kelvins, which is kind of silly to me, but that's the way it is. The amount of material we're going to measure is in a quantity called a mole. And we're going to describe that a lot more in detail later. But the basic counting unit for an amount of substance, and it should be a count. Think about eggs. You got a dozen, okay? That's 12 eggs. You're counting the eggs when you say a dozen. You're counting the particles when you say a mole. we'll talk about that in great detail. Electric current is the ampere, and you will see all of these units we've had so far in Gen Chem 1. In Gen Chem 2, we will talk about electric current in amperes. Luminous intensity is called a candela, and you won't see that until you get to physical chemistry if you hang in there that long. Now, the metric system is all based on subunits, and we use prefixes to define those. The largest one that we're going to use is called tera, and its abbreviation is T, and it's 10 to the 12th. That's a 1 and 11 zeros is how many a tera is. And if we talked about a terameter, it would be 1 times 10 to the 12th meters. My guess is that's the size of galaxies. Huge number. Giga is G. It's 10 to the 9th. And you could have a gigameter. We don't normally talk about gigameters, but gigawatts is the way we measure electric power, and gigawatts. And we actually do have power plants that generate power in gigawatts. Mega is a little closer to home. It's a million. And you could have 1,000,000 meters, 1 times 10 to the 6 meters. Kilo is K, it's 10 to the 3rd, and it's kilometers. So that's the, and kilogram, kilograms, 10 to the 3rd grams was the standard unit of mass that we talked about a while ago. Now the rest of these are smaller than 1. Deci is D, it's 10 to the minus 1, so it's 0.01. So 1 decimeter would be 1 times 10 to the minus 1 meters. Centi is 10 to the minus 2. A centimeter is a unit you use in the laboratory, and you have little rulers that often have 1 foot on one side and something, what it'd be, close to 30, I guess, centimeters on the other side. Milli is 10 to the minus 3. And millimeters, we don't talk about so much, but we talk about milliliters as volume measurements in lab. Micro is 10 to the minus 6. It's the Greek symbol mu. And you can have micrometers, and that is a common measurement. Nano is N, and it's 10 to the minus 9. And typically nanometers is of the order of the size of atoms and particles. Hundreds of nanometers for an atom and a few nanometers for an electron or proton. Pico, 10 to the negative 12. You can have picometers. That's at the range of the subatomic particles, electrons and protons and things like that. And femto is F, and it's 10 to the minus 15th. And femtometer is extremely, extremely tiny. That would be even smaller than atoms or fundamental particles like electrons and protons. We don't normally measure things that small in terms of diameters, femtometers. The only thing that I'm familiar that we do measure in femto is femtoseconds. We can measure time easily into femtoseconds. Now you do need to memorize both of those two tables. And let's look at temperature and define what it is. It's a measure of the hotness of a bulk sample of matter. And it's exactly what you think of. When you think of something having a high temperature, you're thinking that it's hot. And it is. That's what we mean by hotness. It's a hotness for a bulk sample. Although I've seen it done, it's not it doesn't make any sense at all to talk about the temperature of an atom. There is no such thing as the temperature of an atom. It's a bulk sample. Is it temperature of 2 atoms? No, I don't think so, or 3 or 10. But a temperature of a mole of atoms, yes, is a well-defined quantity. Let's look at this, and this, I always try to hit something that I'm pretty sure you've never heard of before. And I've done one with the particulate nature of matter, energy, space, and time. I don't think you probably knew all of that story. But now let's look at an example. Here is nitrogen gas at 1 atmosphere pressure. And if I put a thermometer in it, let's say it's reading 25 degrees. On the other side, I've got this chamber separated from this one by a hole that's about the size of a nitrogen molecule. N2 molecules can squeeze through that hole into a vacuum on this side. Now, if you allow this to go, eventually the temperature over here, far away from that hole, will read 25 degrees. Hey, does that surprise anybody? It was 25 over here, and when the nitrogen gets over here, it's 25 also. That perfectly makes sense. But this one may surprise you. If you put a thermometer up close to that hole, the best temperature, the lowest temperature we've been able to measure is 2 degrees above absolute zero. Why can that be? What in the world cooled the gas and going through that hole? And what in the world heated it back up and going from near the hole to the other side of the container? And the answer is nothing. You didn't raise and lower the temperature by the usual methods of heating and cooling. Let's look at what happened. Here is a sort of a cartoon that's showing the atoms of, or molecules in this case, of nitrogen. The little arrows attached to each molecule is the direction it's going, and the length of the arrow is the speed it's traveling at. So in this sample, this collection of molecules at 25 degrees, you have some very slow molecules and some very fast ones, and all random directions oriented, allowed. And that gives us, that's why we have a temperature of 25 degrees. We have this molecular distribution of molecular speeds and velocity and directions. Now, let's look at the ones that get out of the hole. The only ones that can get out of the hole are the ones that happen to be traveling toward the hole. Of all of this whole collection, what this experiment has done is sorted out particles that are uniform, traveling in the same direction. Now, if this were perfectly uniform, that is, all of them coming out at the same exact speed in the same exact direction, then in fact the temperature would be absolute zero. But, and that's the one way we're going to use to define temperature later on. It's the absence of any disorder is zero temperature. If there's no randomness in the motion, the temperature is zero. So all these particles are traveling in the same direction, but not at the same speed. So that's why we got 2 degrees above absolute zero. Now, what happens, this molecule came out after, before this one, but this one is traveling faster. So eventually this one's going to overtake that one, and it's going to bounce off, and you're going to have the 2 particles bouncing off in two different directions. It could hit straight on, they would just slow each other down. This one would slow down, that one would speed up. If they hit, this one hits this one a little above straight middle, it'll bounce off in this direction, and this one will go off in this direction. Conservation of momentum would tell us exactly where each of these 2 particles went and the direction they went, the velocity they would take. We could do physics on this and do that. And eventually all of these molecules, the slow ones get hit by the faster ones. And eventually what's going to happen is you create this random pattern again. And that's the reason why the temperature over here, after you've had time for many, many, many molecular collisions to take place, we have a random pattern over here that matches the random pattern over here. That's why the temperature over here is 25, just like it was over here. And the fact that there is no randomness, very little randomness in the motion here, temperature is near absolute zero. Okay, you probably didn't know that. But it is the randomness in the motion of molecules of a bulk sample that determines its temperature. So, and again, a bulk sample, like I told you, if we've got two particles, I know how fast they're traveling and the direction they're traveling, I can determine whether they ever will hit or not. If I determine their paths will cross, they could still miss each other. But it might be possible at some particular angle, some particular speed, they would hit at some place in space. From physics, I could tell you exactly when they would hit and exactly how they would go after they hit each other. There's no randomness in that motion. That's why I said one molecule doesn't have a temperature, neither does two, neither does three, neither does four. But you know, they aren't going to hit precisely at an exact angle. They could hit just a little above or just a little below or just a little to the left or just a little to the right. We don't know for sure how they're going to hit. Eventually, that destroys our ability to predict where all of the particles are at some moment later in time. That's the point. Excuse me. That's the point where temperature becomes defined. How many particles is that? I don't have a clue. I just know it's not one or two or three. Now let's look at temperature conversions. Now, there's a formula that you may have learned in high school. I hope you didn't, but if you did, you know, it's something like C is 5/9 F plus or minus 32 or 9/5 F plus or minus. I have to derive that stupid thing every time I use it. But I want to tell you another way that you can do it. If you put a Celsius thermometer and a Fahrenheit thermometer into a liquid and you start cooling it down, couldn't be water because it freeze before we get where we want it. Suppose you put it in, I don't know, ethyl alcohol, and you start cooling that system down. Whenever you take out a thermometer, and read its temperature, when you cool it down to the point where you take out the Celsius thermometer and it reads -40, if you take out the Fahrenheit thermometer, it will also read -40. -40 is the hotness that is the same on both of those temperature scales. So we can use that idea to determine to convert from one temperature to another. So what we're going to do is find out how far we are away from the crossing point of the two scales. And if we add 40 degrees to that scale, whether it's Fahrenheit or Celsius wouldn't matter, we add 40 to that initial temperature. And now that tells us how far we are away in degrees on that particular thermometer from -40. So I add 40 to the temperature, and that's the number of degrees in Fahrenheit. So say I'm at 80 degrees Fahrenheit. 80 degrees Fahrenheit, I'd add 40 to. It would be 120 degrees from the current 80 degree temperature back to the point where the two thermometers would read the same value. Or if I had 80 degrees Celsius, I'd do the same thing, add 40 to it. 80 and 40 is 120 there. Also, it would be 120 Celsius degrees back to where they cross. So this first step is just to determine how far you are away from the crossover point in either case. Now we want to do a unit conversion. And between boiling water and freezing water, water boils at 100 degrees Celsius and freezes at 0. So the difference in hotness of freezing water and boiling water is 100 Celsius degrees. Now, if I take the same values on the Fahrenheit scale, water boils at 212 degrees Fahrenheit. It freezes at 32. The difference between those two is 180. So 180 degrees Fahrenheit is the same hotness difference or temperature difference as 100 degrees Celsius. Now, if you reduce that to the lowest ratio, 5 degrees Celsius would be 9 degrees Fahrenheit. So if we are converting from Fahrenheit to Celsius, we're going to add 40, and then I'm going to multiply by 5C over 9F. I want the Fahrenheit values to cancel. If I were doing the Celsius to Fahrenheit, same thing, I'm going to add 40 to the Celsius value, and I'll get a number of Celsius degrees. But this time I want my factor to be 9F divided by 5C, because I want Celsius to cancel. So in this step 2, you either multiply by 5/9, 5C, divide by 9F, or you multiply by 9F and divide by 5C, whichever way you need to do to cancel the unit you want to cancel and get the one you want. And then the last step is just to undo what you did in step 1. You subtract or add minus 40 to that new converted temperature, and that will give you the temperature of the in Celsius degrees. Now, I do want you to do these checkpoints by the method I showed you here. I know you know the other method. I know that. And there'll be several cases where I'm going to insist that you do it at least in this course by the methods I teach you in this course. Okay? So if you work it the other way, I won't give you credit for it. I want you to understand these methods that I'm teaching you in class because, like I said, I've done it for 50 years. I know the things that work well and the things that cause you to memorize stuff and forget it. I don't want you to do that. All right? All right. So
I
let's
have a
look at this. Yes.
So when you multiply by the Celsius or the Fahrenheit, the number just depends on whether or not it's Celsius or Fahrenheit.
It depends on which one you started with. I'm going to work an example right now and show you. Body temperature is 98.6 degrees Celsius. I wonder what that would read on a thermometer, on a Celsius thermometer. Now, you wouldn't do this. Don't ever do this. Go into the lab and take a Celsius thermometer and stick it in your mouth. Don't do that. You don't put anything in lab in your mouth. But if you did, what would it read? Okay, well, we've got 98.6. The first step was to add 40. When I add 98.6 degrees Fahrenheit to 40 degrees Fahrenheit, I get 138.6 degrees Fahrenheit. That's step 1. Now, step 2 was the one you asked about. So I had 138.6 degrees F. I want my degrees F down here so they cancel. So 9 degrees F goes on the denominator and 5 degrees C goes in the numerator. Now, when this cancels and I do the math, excuse me, I'll get 77 degrees Celsius. The third step is to now subtract or add minus 40 to that value, and I get 37. So you see, by adding 40, doing the conversion to the other temperature scale, and subtracting 40, I get the temperature. That's easy to remember. And just for grins and giggles, if for example, that had been 5/10, that would be half. You could add this to your, add these two numbers together probably in your head and take half of that. You wouldn't get 77, but you get something close to it. And then you could subtract 40 from that value and you'd get an estimate of the value, and you did it in your head. You know what? You just impressed people silly by doing that. They tell you, oh my goodness, it's 92 degrees out here today. It's so hot. Excuse me. Well, you add 40 to that, take half of it, subtract 40, and you could tell them an estimate of what the temperature would be. And you could tell them, well, you know, I'm going to be off about 10%. That would impress them even more. But this is an easy thing to remember. The 5/9 F plus or minus 32 or whatever it was is too easy to forget. And
So what
so
would you do
this
with
is
the
a method I
5?
want you to use.
I'm sorry. What would you? So you want to subtract the 5 degrees Celsius minus the 77 degrees Celsius?
I said, if this had been 5 degrees Celsius and 10 degrees Fahrenheit, then that factor would be 1/2 instead of 5/9. I just said that, so this is something you could do in your head. That's the point. Okay. And this is an easy calculation to do on your calculator. And you know, honestly, I know your calculators, every one of them has a temperature conversion button on it. And, you know, I won't know what you do on tests, but I hope you do learn this method because it's real simple and it's easy for you to do. And, you know, even when you don't have a calculator, you can do this math easy. Okay. What about negative temperatures? Well, convert negative 100 degrees Celsius to degrees Fahrenheit. Well, you're going to do the same thing. You're going to add 40. You get minus 100 plus 40 is minus 60. Now you're going to do the Celsius to Fahrenheit. So I want Celsius on the bottom and Fahrenheit on the top. So 9F divided by 5C. This is going to cancel. I get minus 108 Fahrenheit. And then I add a minus 40 to that. I get minus 148 degrees Fahrenheit. So you see, two different problems, but they're exactly the same method of solution. Add 40, multiply by, do a unit conversion, and subtract 40. That will work on every single case. And then there's one on your checkpoint. I don't know whether it's minus 18 degrees Fahrenheit or what, but whatever it is, that's the one I want you to do. So we've got 2 checkpoints now due tomorrow. Okay. Now, let's look at density. Density is a ratio. It is a characteristic of substances. I told you a while ago, the density of water is 1 gram per cubic centimeter or 1 gram per milliliter. Cubic centimeters and milliliters are equivalent for us. And it's a ratio. A ratio is one number divided by another number. So when I say the density is 1 gram per cubic centimeter, it means if I had 1 cubic centimeter, it would be 1 gram. If I had 2 cubic centimeters, it would be 2 grams. It's a ratio of 2 numbers. Now, there's a disadvantage to this in this sense. If I tell you something has a density of 3.725 and I ask you, what's the mass and volume of the sample? There's an infinite number of possible answers. There's one, whatever I said, 3.725 in 1 cubic centimeter. That's okay. That would be one value. But you could have twice that or 3 times that or 10 times that or 100 times that and still get the same ratio. That's what's important. Now, if all of those numbers are possible and I've got one number divided by another number, let me ask you, what number is the best number in the world to divide by? Yep, 1. You know, I'm not the sharpest knife in the drawer, but I can do that in my head. I can take any number you want to give me and divide by 1. Ain't I smart? All right. So sometimes, since it's just the ratio we're interested in, we can just say, okay, I'm going to use the example where that denominator is a 1. We'll use that a lot. Okay. Now let's talk about measurement again. And there's 2 words, that's accuracy and precision. Accuracy is how close your measurement is to the true value. Let me ask you something. Would you go weigh something if you already knew what its value was? I wouldn't. No reason to. So you can never really know the accuracy of a measurement unless you already know what the true value is, in which case I wouldn't measure it. I just take that true value. Okay. Precision, though, is how closely your measurements agree with each other. And we will believe that if I've got a lot of measurements and all of them are almost the same number, I'm going to believe the true value is somewhere close to that. So I'm going to average all those values, and that will give me an estimate of what the true value may be, but it'll also tell me the spread of my measurements, and that is precision. Okay, let's take a look. Here's some examples. Now this is, say, the true value that we may or may not know at the moment. And here's the measurements that we made in white, and they're clustered all around that value. Now, that is accurate because the average of these values is right on top of the true value. But again, in reality, we might not know that, but these are all clustered right around it. So it's also precise. Means that the precision is very good in our measurements because they're almost all the same value. Now here's another possibility. I make a measurement, the true value is really here. Maybe I don't know that, but the true value is really here. I'm going to think it's over here, and it's really not. But these values are also precise, but they're not accurate. And again, I might not know that. Now this is fixable. Every year, our storeroom person, Ben King, he will go around to the balances in the lab, and he has a special set of weights that he has bought that are exactly 1 gram, let's say. So he puts that exact 1 gram piece of metal on that balance and checks to see what the balance reads. And if it's a case like this, it's reading over here, and the true value was 1 gram, it's reading something bigger than that, then what we're going to do is he's just going to change the internal adjustments on that balance to move all of these readings on top of this one and get this picture over here on the left. So you can recalibrate the balance to make it accurate. And we do that, I think, yearly in all of our labs. We adjust each balance so that it gives a good, accurate, and precise measurement of something we actually know what the weight of it is. Now here's another one that is still usable. It's not very good. If we averaged all these values, we get this value here. So it is precise. It is accurate, I'm sorry, but it's not precise. And so if I made a bunch of measurements, I'd probably get a good value from this balance, but I have to make a lot of them. If I just measured one, I might get this one. That one would be far off. Or I measured it again, I might get this value. That one would be far off. If I just average those two values, I get something over here, which would also be not very good. And so I have to make enough measurements so that adding another measurement doesn't change the average very much. And then I can say, well, okay, that's okay. That's enough. I can quit. And I would get a value. But the point here is you sure couldn't go in and just make one measurement. That would be a mess. Now, this is usable, but not really good. It means you have to take an awful lot of measurements. If these up here, if I took just one measurement, I'd get a value pretty close to the true value. But now here's the worst case of all. It's neither precise nor accurate. And if Ben finds one like this, he'll probably call up our boss and say, hey, we need a new balance for the freshman lab. This one is not fixable. Because you don't want to just internally change it to this over here and maybe still have to make 30 measurements of weight for everything you try to measure. So this one is not so good. And like I say, I'd buy a new instrument there. So you get the idea about accuracy and precision. First of all, accuracy is something you usually do not know. We take the value to be the average of very precise measurements. And if we make several very precise measurements, then we get an average of those that we think is pretty close to the true value, and probably is, especially if everything's been calibrated. So you see the difference between precision and accuracy. Precision is something we can do, and we indicate that by the number of significant figures that we report an answer to. Now, let's talk about significant figures. What is a significant figure? Well, all non-zero digits, if it's not a zero, it is a significant digit. So if you've got a 3 or a 4 or an 8 or a 2 in some position in a number, that number is significant, and that is a significant figure. Now, what about zeros then? When are they significant and when are they not significant? Well, sometimes zeros are not significant and we don't count them. They just mean we've changed units, perhaps. Now, if a zero falls between two non-zero digits, it is also significant. So if I've got 7 and 8, those are both significant by rule number 1. But if I've got a 0 between the 7 and an 8, then that is a significant 0, if it falls between significant digits. Now, if it falls to the right of a side of a number with a decimal, for example, 1.2 and 1.20 is really the same amount, same measurement, but they differ in, we added that 0 because if I say 1.2, that's 2 significant figures. If I say 1.20, that's 3 significant figures. So if I got a 0 and show a 0 to the right of a decimal, the only reason we'd put it in there is to mean we want it counted. So if it's to the right of a number with a decimal point, then that 0 is significant. Now, if it's, say if I had 2 or 20, those are not the same number. Why did I put the 0 in there? I put the 0 in there to tell you I wanted you to think of 20 instead of 2. So I put that 0 in there to do that. That 0 is important to the value of the number, but it is not a significant number. So the 0 to the right of a number without a decimal point is not significant. Or zeros before a decimal point. I mean, you don't want, if you say 0.20, how many significant figures? Well, the 0 in front of the decimal is not there. It's not important. It was just put there for convenience. You could write 0.20 if you wanted to. Everybody would know what you said. But if you put 0.20, everybody knows that you didn't just forget that digit in front of the decimal place, that it was a 0. So the 0.2 and 0, the 2 and the 0 would be significant, but the 0 in front of that would not. 0.20 would not be, the leading 0 would not be counted. Now, here's something you need to be aware of, because your calculator is going to do exactly what I'm saying here. So when you are working out a problem, you have to be careful, because the calculator is going to do an order based on the way you enter the numbers. Now, the order of performing calculations, the very first thing that's going to happen is the calculator is going to look for grouping symbols that you put in. You might put in a left parenthesis. So it's going to keep on searching until it finds the right parenthesis matching that. And it's going to do all of the calculations inside that. If you've got them nested, you know, you got parentheses and then you got brackets and then you got braces and things like that, it's going to work out the most inside one first, and then it's going to work out the next one, and then it's going to work out the next one. So it's going to do groupings from inside out. That's the first way it's going to set the problem up. So if you've got parentheses and you've entered in your calculator, remember that's the way it's going to do. It's going to work out the groupings on the inside first. Then it's going to take that value and combine it with the groupings of the next grouping and do those math operations and so forth, all the way to the outside. Now within a grouping, when it does calculation, you can do addition, subtraction, multiplication, division, square root, cube root, square, cube, raised to the 5th power. Powers are the first thing, and roots are the first thing it does. Now it's going to look in that series of calculations it has to do. If one of them is squared, it's going to do the square first. If one of them is take the square root of this next digit number, well, it's probably going to do them left to right. If the square came first, it'll square first. And then if the cube root is later on, it'll do the cube root. And it'll save both of those results to do the rest of the calculations. So raising to powers or taking roots is second priority. Actually, the first mathematical priority. The first one is the first order grouping is just to put things together into smaller pieces. Break that big problem up into little problems. Then the next operation it'll do is multiplication and division. And it will do them. It can do them in any order that you want to do them. I'm going to do left to right because when I'm entering numbers in my calculator, I'm going to take my index finger on my left hand and follow along the numbers as I put them in the calculator and the operations that I put in the calculator. I'm going to do them left to right so that I don't forget one of them. I'm not going to do all the multiplications first and then all the divisions, or all the divisions first and the multiplications. I'm going to do them in whatever order they appear from left to right. And then the last thing it does is addition and subtraction. And we're doing the addition and subtraction again, left to right. Let's do the round off rules and then we'll call it a day for this segment. And we'll pick up again maybe 10 minutes later. Okay. Let's see, we're starting lab at 10, right? I think that's right. Okay, multiplication and division rule. This one, everybody knows. You come out of high school knowing this one. When you're multiplying two numbers together or dividing numbers, the rule is the answer has the same number of significant figures as the least you used in the calculations. So if you've got a digit, if you've got a number somewhere that's got 3 significant digits, and another one that's got 2, another one's got 4, and you do that math, when you push the equal sign, the calculator is going to give you maybe 8 different digits, decimal places perhaps, on that number. But you want to round it off to the least number of significant figures that you use. So if I used a 3 and a 2 and a 5, then the answer would round off to 2 significant figures. So multiplication and division is easy. Everybody knows that. Everybody gets it right. The problem is with the addition and subtraction. The thing you've got to remember now, what would be the very last operation your calculator will do? It's going to do raised to powers and roots first. It's going to do it multiplication and division next. And the last thing it does is addition and subtraction. Remember how you added numbers together in 3rd or 4th grade? When you got ready to add numbers with decimal places in them, you lined them up over top of each other so that the decimal points in all the numbers lined up vertically. And then you added the numbers together. Now, it's clear that if you've got a number in there that is 0.6, and you've got another number that's 0.28 and another number that's 0.375. You've got, when you line them all up, the only real decimal place that is accurate or precise is the first decimal place, because one of your numbers was 0.2, had only one decimal place. One had 3 decimal places, the other had 4. So your answer is going to round off to the least number of decimal places. People miss this all the time. You're going to have it on an exam or a quiz, and well, both probably. My prediction is half the class will miss it. I hope I'm wrong. If you paid attention to what I've told you and you do the checkpoint problems and you get them all right, you will be one of the half of the class that gets them right and gets the points. Remember, the answer has the same number of decimal places as the least number of decimal places you used in the problem containing addition and subtraction. You're rounding off by decimal places, not by significant figures. And I can make problems all day where you will miss an addition subtraction problem because you applied the multiplication and division rule. Now, what if you're rounding off numbers? What do you do about 5? If you've got you're starting to round off a number and the digit that you're going to drop is less than 5, you drop it. If the rest of the number is greater than 5, you advance this number to one bigger. What do you do if it's exactly 5? That's a rare case. But what we do is, if that is exactly 5, that is, when you push the calculator, you get 27.25, and that's all it shows you. No other zeros. If it shows you 27.250001, you round up. If it gives you 24.99999, you drop. You're going to do 25.0 if that were the numbers. You're going to drop the digit if it's less than 5, the round off part. You're going to move the number up 1 if it's greater than 5. If it's exactly 5, what you do is you look at the number you are affecting, the one you're rounding off to. If that's even, you just drop the stuff. You just drop it. Like if you were rounding off 25.55, you would take that 5 and you would round that up to 25.6, because that you're dropping exactly a 5. You want the digit you're leaving to be even. Okay? So now, how often does this occur? Only when you make it occur, generally. Very unlikely to happen that you get exactly 5 as your round off, as your part to drop. Okay? Now, you need to carry units in your calculation and check to see that your answer is in the correct unit. Okay, there's a checkpoint on this. And so I wanted to get to this before we stopped. Here's a set of problems. Now, if I'm looking at this, this is multiplication and division. This is multiplication and division, and we're subtracting the two. Now, what I'm going to do is the multiplication and division first. So if I did this multiplication and division, this is what you would get if you took this number times this number and divided by this number. You would get this number. Now, suppose this was the only problem I have. What would I do? I'd say, okay, 1, 2, 3, 4 significant digits. 1, 2, 3, 4, 5, 5, and 6. So I would round off to 4 significant digits. 1, 2, 3, 4. I would round off to there. Okay, I'm not rounding off. I'm just noting where I would round off. Now I'm going to do this 4 significant digits is 3 decimal places here. Now I go over here, I do the math. I take this number, divide by this number, I get this one. 1, 2, there's 5 significant digits and 6, so I'd have 5. 1, 2, 3, 4, 5. If I were rounding off, I would round off there. But now, the 5th significant digit is also, in this case, 5 decimal places. So I'm going to do a math problem, one of which has 3 decimal places and one which has 5. How many decimal places would the answer have? You're right, 3, the smallest. So if I add this number and take this number and subtract this one, I get 0.559 and whatever. I don't know what it really was, but I do know I need 3 decimal places in the answer. So it has 3 significant figures, 3 decimal places in the answer. I want you to notice now, please notice. The answer has 3 significant figures. There is not a number in this bunch that has 3 significant figures in it. But that's what we get when we round off correctly. Do not round off this number to 1.076 and do not round off this number to 0.51667 and then subtract those 2 numbers. Take this whole number with all of its digits and subtract this whole number with all of its digits. Round off the answer to 3 decimal places. And that in this case would be 3 significant figures as well. Okay, you've got a problem like this for the checkpoint, and that would be all we'll do for today. Okay, so I'm going to